Hello, everyone. Welcome back. It's been a while since we've had a live session. My name is Matthew. I am one of the instructors for our online classes, and we will just say a quick hello, and then we'll get started with your questions. I'm going to introduce Professor Impey, who will say hello, and then we'll get going.
Yes, welcome everyone. We took a little time out. I actually had some travel. First time I was on a plane since January 2020, before pandemic, in going to Washington, where we did a virtual reality exhibit of our major telescopes and space facilities in a center we've set up 2 blocks west of the White House. So that was a lot of fun. Meanwhile, the world of astronomy moves on, so welcome everyone from either of the online classes or just anyone who happens into this stream and the associated YouTube channel, and we can get started, so the floor is open for your questions.
Excellent. The very first question is from Cornan, who's on with us live. Would it be possible to drill an elevator shaft through the moon?
Technically, yes, but actually the technology is pretty much beyond us. If you look at what the deepest mine shaft or elevator shaft, if you like, has been drilled on the Earth, I don't know the exact number, but it's something like 10 or 12 kilometers. It's not very deep. It's just a pinprick in the Earth's surface. If you made an analogy of the Earth as an apple, we've drilled less than the thickness of the skin down into the Earth's crust. And that's just because the technology of drilling through deep rock is extremely hard. And the same problem would face us on the moon. The moon's a quarter the size, but drilling all the way through the moon would be the same as drilling a quarter way into the Earth's crust and mantle, and that's far beyond our capabilities. So I'd have to say technically this is pretty much beyond us and will be beyond us for decades.
Excellent. We've had a few people talking about how to get into astronomy. So can you talk a little bit about sort of pathways into the field of astronomy, either through an undergrad, or maybe you did an undergrad and have a master's program? Can you just talk about some of the different pathways to astronomy in the professional world?
Sure. I mean, the classic path to astronomy is really through physics, because there are far more undergraduate physics degrees, Bachelor of Science degrees, than there are undergraduate astronomy degrees. And I'm talking now worldwide, not just in the United States. So the classic path to astronomy is through physics, whereas an undergrad you may take a couple of astronomy courses, but you're getting a foundation of the physics that underlies astrophysics. Essentially, astrophysics is just physics applied to the universe, and that's what astronomers do. So that's the classic path. And in any case, to be a professional astronomer, you need a lot of math and physics. And so you need a program that has that as an undergraduate. It's also possible to get into astronomy through a related field, such as geology, geosciences. And chemistry is possible. Biology is less likely, because you just simply won't have much physics in a biology degree. So that's the classic path. Now you can transfer across into astronomy using a master's as a vehicle. So there are a number of master's degrees now, including online masters in astronomy, that give people a lot of background that they might not have got as an undergraduate, and they would prepare them for a PhD program. So with either an astronomy bachelor or physics bachelor, it's easy to go straight into a PhD program in astronomy. But you can transition through a master's program, which will give you the requisite background. And those are the basic pathways. A less likely pathway, but possible, is through certain types of engineering, space engineering, electrical engineering. But again, you're not likely to have got most of the physics you need to do well in a graduate program, because most graduate programs in astronomy, if you're studying a master's or a PhD, there's a lot of physics there too. So those are the standard routes into astronomy, and they can be a little circuitous depending on what your undergraduate training was. But persistence, application, and just taking the right classes will get you there in the end.
All right, the next question is from Lawrence K., who's on with us live. If light from a distant galaxy is redshifted, does the loss of energy somehow add to cosmic expansion? Does it become part of dark energy? Is energy conserved in an expanding universe?
The question of conservation of energy in an expanding universe, that's an interesting one. You can view the Big Bang as having imputed or given an impulse to the universe which gives it an enormous amount of expansion energy. But correspondingly, it has an enormous amount of gravitational potential energy from the mutual attraction of all the mass in the universe. So in that sense, it's a zero-sum energy situation. When light travels through expanding space-time, the wavelength is stretched as the space itself expands. And so it is a loss of energy, in fact, because going to longer wavelengths means a lower energy photon. And in fact, if you look at the way the universe evolved, there's a difference in the rate of the mass energy or the density changing and the radiation energy density changing. I think we just lost the stream. Matthew, did we just lose the stream? I'm going to keep talking, but I have a feeling we crashed and lost the stream. So we may have to pick up this question. Well, I'll finish the answer, however. So when space expands, the density of matter diminishes. The mass is diluted as the bigger volume goes over time. And when radiation is in that volume, the volume increases, but also the wavelength goes down. And so the energy density goes down as the fourth power of the size of the universe, whereas the density only goes down, of matter, goes down as the third power of the size of the universe. So there's a difference in that regard. I have a feeling we've lost our stream, so we'll just be on a long pause here while Matthew gets it back. Okay.
Hey, sorry about that, everyone. My computer froze and I am back now. My apologies. All right. So we are back, and the next question is from.
Just for a second, I kept answering the question. I have no idea if we were still recording at that point.
Yep, we're still going right now, as a matter of fact.
Okay.
So let's just keep going. All right. So the next question is from Brittany, who would like to know, does the mass of a planet affect the gravity of its own planet? Does the mass of a planet affect the gravity of itself? So can you talk about the relationship between gravity and mass, I guess, is the question.
Sure. Gravity scales directly as mass because the gravity of an object, and the surface gravity, for example, depends on the size. So the overall mass of an object determines its gravitational force, as seen from a distance. But the surface gravity depends on how that mass is distributed. And so, therefore, it depends on the density of the object. So we can distinguish between total gravity, which is the force exerted by the entire total mass of an object, and what the surface gravitational force is, which depends on how that mass is distributed, essentially on the density of the object and its radius.
Excellent. All right. The next question is from one of our live participants who would like to know, if I have two entangled particles in different locations in space, What would happen if one particle fell into a black hole?
Um, this is a theoretical construct or question that is of great interest to theoretical physicists and of great interest to black hole physics. The simple answer is we don't know the answer because clearly entangled particles are sharing quantum information. They have coherent information. And yet information is lost when an object falls into the black hole. There's one theory of black holes that suggests that the resolution of this situation is that there's a firewall around a black hole, which essentially is a high radiation environment created by these entangled particles where the information is actually destroyed. So the best guess about entangled particles and the event horizon of a black hole is that the loss of one of the particles into the black hole destroys the entanglement and destroys the coherence of the information, because information is indeed lost in a black hole.
All right, the next question from one of our live participants is from, let's see, okay, what makes a neutrino interact with something if it decides to interact? Why do they interact sometimes but not always?
Well, that's a good question. Neutrinos are subatomic particles, they're fundamental particles. There are three flavors of neutrinos: the electron, muon, and the tau neutrino. We do know that neutrinos have mass, although the actual mass has not been measured. Neutrinos have been observed in physics experiments, like the deep mine experiments at several locations around the world. Neutrinos have been observed to oscillate, and that is, they change or move between one species and another. And that allows physicists to get a sense that the neutrino does actually have mass, although all we can determine is combinations of the mass of multiple species, not any individual mass. So neutrinos oscillate, and they therefore have mass. Neutrinos have a very small interaction cross-section, but it's not zero. So the issue of whether a neutrino interacts with matter is basically a function of its cross-section. And the very, very low cross-section compared to a particle like even an electron, and certainly like a proton or a neutron, just means that the neutrino can essentially penetrate vast amounts of material, the Earth or planets or large amounts of solid mass, where the probability of an interaction is actually still very small. So it's just a very tiny fraction of neutrinos that will interact with matter.
And the next question is from, again, one of our live participants. So can you talk a little bit about your views on alien life? Do you believe they exist, and what are the odds?
I do, as a matter of conjecture, because we have no evidence. And as for the odds, I mean, that's really hard to tell. At this point, all we know is that planets form as a natural byproduct of star formation. So it's natural to have planets. We've found thousands, almost 5,000 exoplanets at this point, and the statistical studies suggest that there are at least as many planets as there are stars in the Milky Way and by extension in the universe. So we have an enormous number of potential sites for life. Even if you take then the small fraction, the relatively small fraction that are Earth-like in size and are in what would be called a habitable zone of their star that they orbit, which is a region, a distance range from where water can be liquid, you're still at a very large number. The number of habitable spots in the Milky Way is estimated to be 10, perhaps 20 billion. So with all those sites for life, which essentially have all the necessary minimal ingredients, which is energy source from a star, liquid water, because water is quite an abundant molecule in the universe, and carbon material, because planetary material includes a lot of carbon compounds, then there's a good reason to expect that life will exist on some number or some fraction of these locations. We simply have no way of estimating what that fraction is. It could still be a very small fraction if the process by which simple chemical ingredients get together to form the first metabolism and the first cell is extremely unlikely, or extremely complex set of events that end up being unlikely in the aggregate, and that we simply don't know. So this isn't an empirical question. It's one that we can't really project or predict from theory and the speculation is just that. So we will simply not know the answer until we look for life. If we find microbial life on some of the Earth-like planets we've already discovered, the fraction of them that we find life on will project to probably a very large number of sites for life in the Milky Way and the universe.
All right, with all of the news and speculation about life, I think it can get kind of confusing sometimes. Natalia would like to know, officially, has life actually been found on any planet outside of the Earth? Is there already data, for example, of bacteria on Venus or Mars or any other planet, or are all of these just conjectures still?
No. As we speak, in 2021, there is no life known anywhere beyond the Earth. The Earth is the only known living planet. In the solar system, we've seen evidence of places that might host life. They have the potential to host life. Subsurface Mars would be one example. But we have no evidence of life, either current life or extinct life on Mars or any other place in the solar system. And for the exoplanets, our knowledge of them is still quite primitive. We've basically measured global properties such as mass, size, and in a few cases, a global composition to say that they're a rocky planet or a gaseous planet. Our techniques are not quite good enough to detect microbial life as having altered their atmospheres. But that is going to come within a few years, actually, from various large telescopes that are being built, and also a space telescope of the James Webb that's due to be launched in December. So I think we're going to get the experimental techniques to answer the question within a couple of years.
Excellent. So the next question is, again, from one of our live participants who would like to know, sorry about that, why are, oh, this is kind of a, I guess the question is how do things get their names? So can you talk a little bit about, so this one asks about why are the first 6 months in our calendar named after gods and the last 4 are named after numbers. So how do things like calendars and planets and things get their names? There are obviously astronomical connections between all of these things. So how do we name things?
Right. I'll answer this as really 2 separate questions because it is 2 separate things. The issue of calendars is an interesting one. It's a historical thing that has evolved over thousands of years. In the Western calendar, the one we use, which originally came from the Romans, and it's the Julian calendar essentially, with an alteration by Pope Gregory in the 14th century, which means we call it the Gregorian calendar. This was the calendar that we're familiar with 12 months. The first 6 months were named after gods, primeval gods. Janus, the god of doorways and beginnings, Februa, the god of purification, Mars, the god of war, of course, and so on. These are gods that were known to cultures going back thousands of years. The last 4 months, named after numbers, is interesting because these Latin words, of course, December is the Latin for 10, November is 9, October is 8, and so you have the last 3 months named after 8, 9, 10, and yet they're the 10th, 11th, and 12th months. And that's because the earliest Roman calendar only had 10 months. And so they were just literally counting them off in Latin. And eventually, around the time of Julius Caesar, the calendar got longer and had 12 months. And so it's a relic of early Roman calendars that those last few months have number names. Now, there are a couple of months in the middle that have a third reason for their naming, and that's July and August. July and August were named after Roman emperors, naming months after themselves. July for Julius Caesar, and August for the Emperor Augustus, who followed Caesar. So these were just power grabs, if you like, by a Roman emperor to name months after themselves. So the calendar naming of the months is an interesting relic of primeval gods, egotistical Roman emperors, and the simple Latin counting of a very primitive calendar with only 10 months. To answer the question more generally of how astronomical objects get their names, there's actually a fairly rigorous procedure for that. The International Astronomical Union is the governing body of international astronomers. It's based in France. It has many members, I think 14,000 worldwide, astronomers in 150 different countries probably. I'm a member, and many of my colleagues are. And they have meetings every 3 years which gather the world's astronomers where they talk about everything. Meanwhile, there are groups, committees, commissions within the International Astronomical Union that deal with the naming of things. And they're quite rigorous about this. You're not allowed to name objects after yourself. You're not allowed to name them after sort of pop culture icons or famous people or rock stars or actors or anything like that. You can do that, but it won't have any validity, and eventually the international governing body will rule on it. So typically, naming conventions have been fairly conventional and conservative, and people have named things after Roman and Greek gods. And so most of the objects in the solar system, going down to small things like asteroids, Ceres is a Roman god, are named after gods. Now once you get to stars, the naming is a little different. Stars are named by their constellation. If they're bright enough to see, then they're named after the constellation with a number in front of them to say what order of sequential brightness they are in that constellation. So 61 Cygni is the 61st brightest star in the constellation Cygnus, for example. And that's the naming convention for the bright stars. Once you get to faint stars, then they have to have positional designations, because of course there are billions of stars in the galaxy, and the numbers get pretty crazy. And it's a similar situation for galaxies. The brightest galaxies tend to have names: Andromeda, Reticulum Galaxy, Whirlpool Galaxy, and so on. These are the iconic objects that were typically named and discovered by Messier in the late 18th century. So the Messier objects are given their Messier designations, M31, M10, M101, etc., and they're known that way. A few have names, as I mentioned, and then when you get to the fainter galaxies, they're just again given position designations because there's too many. There are billions of galaxies in the universe. So the naming is done in a fairly systematic way, but for the vast bulk of objects in the universe, the naming is essentially a position designator which would tell someone where to find that on the sky.
Excellent, thank you. The next question is from one of our live participants. Sohini asks, or Sohini Mahapatra asks, can astrology, or how is astrology be related to astronomy?
Historically, astrology and astronomy were quite closely related because people didn't have a scientific explanation for the sky and the objects in the sky early on. There was a lot of superstition, and so it's the sort of era of superstition that leads to the idea that celestial objects, astronomical objects, can control us somehow from afar, because they were mysterious objects that seemed to influence us in some way. Formal astrology as a system for making predictions evolved, I think, in Roman times. Wealthy Roman people would have their horoscopes cast. They would have their own astrologer, maybe, if they were really rich. And these astrologers were making predictions about their life based on the position of the planets and the stars. Remember, the Romans were extremely superstitious, so believing in astrology fit with their overall superstitious behaviors. Eventually, even in the late Roman times, astrology spread to the common folk, and so everyone sort of had the idea of astrology. And astrology stayed part of the astronomical landscape, broadly defined, and through the Renaissance. And some of the most famous astronomers of the classic period of time, from Copernicus to Newton, practiced astrology. Kepler did, Brahe did, and so on. I don't think Galileo actually did. But it was not unusual for an actual astronomer in those days to practice astrology, usually as a way to make money, to make a living. As you move into the modern day, there are definitive experiments, a number have been conducted, all published and visible to anyone who wants to look them up. Use Google Scholar, I suggest. Have debunked astrology. There is no way that the influence that either your personality or the events in your life are in any way determined or prescribed by the position of the planets, or at the time of your birth or afterwards. There's no physical mechanism by which this could occur, because gravity is really the only mechanism we need, and the gravity exerted by the planets compared to the gravity exerted by the Earth and the nearby objects, even the moon, is far, far greater. These planets essentially have no influence on us physically. So astrology has been pretty clearly debunked and heavily debunked over time. It remains in the popular culture where, again, it's a mild form of superstition that I suppose you might say is harmless, but astronomers do tend to get slightly annoyed by its pervasiveness.
Is there any information on where the term astronomy came from and how it differentiated from astrology? Because, we have biology, that's the study of life. And so
Yeah,
I think some people just get confused by the ology at the end.
right. I don't know the etymology of the word, so I don't know the formal, Latin or Greek root distinction between astrology and astronomy. But yes, the naming confusion is a serious issue.
All right. The next question is from Korat Yug, who asks, how big can solar flares get? And are we ready for one to impact the Earth, or let's say a big one?
Solar flares occur all the time, routinely, and the average solar flare that might occur monthly or annually is relatively mild in terms of its effect on us, and even in terms of its size. I mean, the average solar flare can indeed produce a prominence on the sun's surface that is bigger than the Earth. But remember, the Earth is 1,000 times smaller than the sun, so that's still a very small fraction of the sun's diameter that these flares occupy. And they also change the energy output of the sun by a tiny amount, even at high energies. So the average solar flares do have some impact on us because they throw an extra wave of particles and cosmic rays and high energy radiation into space. And so it can lead to sort of what we might call space weather, where there's a higher level of static interference or interference with telecommunications. That's a typical solar flare, the kind that occurs every year or so. There are, however, things called superflares. And in the history of our sun and in other stars, we've seen evidence that superflares occur on timescales of thousands of years, typically tens of thousands of years. There's indirect evidence that our sun has had superflares in the past, and these superflares are dramatically more powerful events. They release thousands or tens of thousands of times more radiation than a normal flare. Luckily, they're that much rarer as well. But if a superflare occurred on the sun, it would dramatically and catastrophically affect telecommunications. It would probably bring down the electric grid in any countries that were receiving the full first brunt of those solar particles, and it would bring down or zap telecommunication satellites around the Earth and really cause complete chaos and havoc. Unfortunately, it's very hard to predict when a superflare will occur, and we haven't had one for a while. So our early warning systems are not that great. We would get a little lead time. It's not just the 8 minutes that it takes light to travel from the sun. We'd have a lead time of hours, perhaps a day, to get ready. But if our systems are not hardened well before a superflare occurs, then modern civilization would be in kind of big trouble.
The next question is from Wendy Traver, who sent an email asking, do cosmologists have an explanation as to why the laws of nature seem to be bifurcated into quantum and macro theories?
No, we don't really have an explanation. Going back to the origin of the quantum theory in the 1920s and 1930s, there was a principle called the correspondence principle, where it was understood that all the strange and bizarre behavior of the quantum world, the indeterminacy, the superposition, the coherence and entanglement, these effects disappear on larger scales. Essentially, when you take large aggregates of individual particles or atoms and observe them on larger scales as collections, then the bizarre quantum effects that are visible in single particles or single systems average out or smooth out, and you get macroscopic, fairly predictable behavior by classical physics. So there's a correspondence principle, which means as you scale up the size of a system, you start to recover classical physics in a smooth way. That's not to say that we fully explained the origin of all these quantum effects, because seen in their fullness, where you do study individual particles, There are some very strange phenomena going on here. There's action at a distance. That's probably the strangest of all, which appears to violate causality at some level because we have instantaneous effects across significant physical spaces, something that's not possible in classical physics. So there are some aspects of quantum systems that are simply not reconcilable with classic physics.
All right. Thank you very much. The next question is from, I guess, a related question is from Dan Cooper. How extensive was the recent coronal mass ejection from the sun? And, is there any way to predict these coronal mass ejections and how they'll affect the Earth?
The most recent coronal mass ejection was a sort of decadal event. These are events that don't happen all the time, but this was not a particularly dramatic one. It was not catastrophic. We would have heard all about it if it had taken down telecommunication systems. And the answer about predictability is unfortunately no. The sun is a sort of seething fusion plasma ball where the energy percolates outwards from the core where the radiation is produced. It takes typically tens of thousands of years for a photon in the gamma ray core of fusion of the sun to percolate and degrade in energy out to the photosphere where we see it as a yellow photon of light. So there's a long diffusion timescale, and the details of the behavior of the surface are to do with magnetic fields. Those magnetic fields are fundamentally chaotic, but of course they have order, as we can see them looping in and out with pairs of sunspots. So this mixture of order and chaos of the sun's magnetic fields, which is underlying flares, sunspots, and coronal mass ejections, is fundamentally unpredictable. It's just complicated enough we can't predict it. So unfortunately we have no mechanisms to ward off or give advance warning of a CME.
All right, thank you very much. The next question is from Hernan Reyes, who sent an email. The Lucy mission is going to the neighborhood of Jupiter, and it's imminent. I have read that it will explore asteroids that orbit or are orbit near Jupiter. Can you please talk a little bit about this Lucy mission and the aims and purposes of it?
Yeah, Lucy is an interesting mission. I'm not sure exactly when its launch date is supposed to be, but it's looking in the sort of vicinity of the asteroid belt and the vicinity of Jupiter. People don't always realize, but the asteroid belt, covers this substantial radial distance in the sun. It's in that large gap between Mars and Jupiter, but it covers a significant range. And Lucy's going to explore that region between the outer edge of the asteroid belt and the region that is Jupiter and its moons. There are interactions there because asteroids are continually being scattered out of the asteroid belt, and many of them will, of course, be scattered inward to the sun, but in the outer part, many of them are going to be scattered outward toward Jupiter. So the mission is going to try and catalog the size of this effect and find out how many asteroids are scattered out of the belt itself to Jupiter Jovian distances, and also in the other direction too. It's possible, for example, that a moon of Jupiter could be a captured asteroid. The probability of that seems low, but it's not insignificant if many asteroids are being scattered out to that distance. So Lucy is going to do a sort of hybrid mission, looking at the Jovian system, but also looking at the outer parts of the asteroid belt and cataloging them with very good precision with its cameras.
The next question is from Razvan, who is from Romania and on live with us. If the universe was so dense right at the Big Bang, why didn't it at the time collapse into a black hole, and why hasn't it all collapsed into a black hole?
Well, that's an interesting question. And so formally, the Big Bang, all we can do really is trace backwards towards the Big Bang. I mean, to be honest about the theory, the Big Bang theory, it does not explain the Big Bang state. It does not explain the singularity or the origin. All it is a physical description of what happened afterwards, an expansion from an ultra-dense, ultra-hot state. So, did the universe formally correspond to a black hole? And did it have a singularity? Those are very interesting questions. If you simply extrapolate backwards from the known expansion history back towards the origin, you do indeed project a situation where there would have been a singularity. So formally, at the inception of the universe, it did satisfy the criterion of being like a black hole. But a black hole is a static, stable object in the current day universe. And the Big Bang, of course, was a highly dynamic event where space-time was expanding far faster than the speed of light. So I don't think we can really analogize it to a black hole.
All right, a couple people have mentioned the fact that William Shatner, TV's Captain Kirk, was launched into space today. Can you talk a little bit about what your opinion is on private space travel?
Sure. I watched that earlier today. Didn't take very long. It was a 10-minute flight, 4 minutes of zero gravity. And so very exciting for those of us who grew up on Star Trek to see William Shatner at age 90 become the oldest person ever to be in space. People are quibbling about whether the Blue Origin's private space flights are making astronauts. Formally, that flight went to 350,000 feet, which is above 60 miles or 100 kilometers. That's above the Kármán line, the internationally designated boundary to space. To put it in perspective, however, that is far below an Earth orbit. And in fact, it would take 10 or 12 times more energy in a rocket to get beyond where they went today to get into Earth orbit. So these are little jaunts to the edge of space, I guess I would put it. And Shatner himself had a nice answer to this question of people quibbling over whether these people should be called astronauts. He said we should be called astronauts with a little a. So he had some humility about it. But it was nice to see him in space as the oldest astronaut. My opinion about the private space sector is mostly positive, but a little mixed. There's obviously been a lot of debate in the media world and in the blogosphere and so on about rich billionaires indulging themselves with private space travel while most of the world is poor and so on. And that's a good point. So I can mostly take a positive view over it because what they have done, what SpaceX and Blue Origins have done that is remarkable, is they've changed the paradigm of rockets and getting into space. In the Apollo era, and even with the space shuttle, which was nominally reusable but was so fragile, those heat tiles and the cost and the inability and the difficulty of getting those initial rockets fished out of the water and refurbished was an incredibly expensive proposition. And Apollo simply jettisoned a lot of hardware. What these two companies have done is make a fully reusable primary stage rocket. And if you watch these launches, then one of the most amazing and impressive things is to watch that first stage just parachute down out of the sky and then turn its rockets on and land back on its launch pad intact to be reused again. And I think the Blue Origin's rocket today was the 4th time they've used that vehicle. And that's a game changer because, of course, it lowers the cost enormously. So they're making a new economic model. And while it's still true that it's a tiny number of people, and if they were paying, they'd have to pay a lot of money to go up there, that number is going to come down dramatically. So I think it is an interesting point in history to have these two companies competing and both having changed the idea of how rockets work and their viability and economics and opening up a new sector of business and industry, of course. That's worth saying. But it's also good to keep it in perspective. Shatner, for example, as he got back out of the rocket, said, everyone needs to do this. And he was excited, of course. He was talking about his own experience. Well, you could take a pause and say, well, everyone is not going to be able to do this. There's 2 billion people in the world that need fresh water. There's 4 billion people in the world that need a COVID vaccine. That's what the world needs, and rockets are not going to save us, and rockets are not going to get to be an experience for more than a few people for quite a while. So it's good to keep it in perspective.
You talked about it briefly, but can you explain sort of the significance of the Kármán line?
Right. So the boundary of space was defined. Kármán was an airspace pioneer from the early part of the century. I think he was Hungarian. And at some point, NASA and the other space agencies had to agree on a formal designation for space. Obviously, it's arbitrary because there is no fixed boundary. As you go up, the atmosphere gets thinner and thinner and thinner, and certainly at the elevation that the SpaceX and Blue Origin's rockets and also the Virgin Galactic rockets go, you're in the blackness of space, so you look like you're above most of the atmosphere. But the atmosphere is not zero. There is some atmosphere up there. So it's kind of arbitrary. But from going back 50 or more years, the Kármán line, 100 kilometers up, it's obviously a round number, so you can tell it's arbitrary just by the number itself, roughly 60 miles, has been taken to be the formal boundary of space. And that's what these companies have aimed for, to get to say in their short parabolic flight that will literally just last 10 or 12 minutes, that they have sent astronauts into space. The purist might say a real astronaut is someone who goes into Earth orbit, which is substantially higher. That's at 250 to 300 miles up, where the Hubble Space Telescope is, for example, or the International Space Station. And that's a much harder proposition. Now, the quibbling over this has extended to Virgin Galactic. Virgin Galactic actually, for safety reasons, and they've had a fatal accident in their past, had to descope or tone down the power of their rocket engines. And so the Virgin Galactic flight that happened earlier this year didn't actually get to the Kármán line. It was somewhat below it, because that's the best their rockets could do. And so in the sort of highly competitive world of private space sector, they got an asterisk by their flight, whereas Blue Origins definitely get above the Kármán line with their rocket.
So the final question related to this is, if invited to be one of the dignitaries aboard one of these spaceships, would you go on one of these launches, or would you pay to fly into space on one of these capsules?
Sure. I mean, as a personal question, absolutely. I mean, if I was invited, as a freebie, and it's absolutely no question about it. If I had to pay, it would sort of be a question of how much. The projection in the industry, this budding private space industry, is that soon enough the cost of going into space, this joyride type of space flight, where it's really quite short experience, is going to come down to the cost of a sort of fancy cruise, which is maybe $20,000. People drop that kind of money on cruises all the time. And for a once-in-a-lifetime experience, yeah, I would probably do that too. It's fairly safe. We should bear that in mind, that it's not risk-free by any means. You're sitting on a rocket, you're sitting on highly volatile rocket fuel. But both the SpaceX and Blue Origin's vehicles have capsules with escape mechanisms to liberate themselves from the rocket that's pushing them into space should something go wrong. So they're designed with some significant margins, of course, in the rocket itself. And if you're paying attention to these flights, if you watch them, you'll notice there's a time a couple of minutes into these flights where there's something called max Q. And that's essentially the point where the acceleration and the stresses on the rocket are at their maximum, where the thrust is at its maximum, where the change of speed is at its maximum, and you're also still quite in thick atmosphere, so there's potential instabilities. That's the maximum danger for these rockets, is that period of time. And people who work on these systems breathe a little easier once they get past that max Q phase. There was also max Q for Apollo and for the space shuttle, and all rockets have it, and it's usually a few minutes into a flight.
The next question is from Wendy Traver, who sent an email. It seems counterintuitive that as a star ages and uses up its primary fuel, hydrogen, it gets hotter. Can you explain how that works?
Sure. So it's a good question, and it's going to happen to the sun. The sun is, as it's now halfway through its main sequence lifetime, is going to start getting hotter. And that heat is actually going to have a pretty serious effect. We don't have to wait till the sun dies in 4 or 5 billion years for the Earth to be fried as it goes into the red giant phase and tosses off a planetary nebula. Basically, the best guess is that within about 500 million years, the sun will be burning hot enough that the biosphere will be toasted, which is to say the surface temperature of the Earth will go above the boiling point of water. And the reason this happens is that as the star converts hydrogen into helium, it's continually reconfiguring itself. Stars are subject to a balance called hydrostatic equilibrium. At every point within a star, there's a balance between the inward force of gravity and the outward force due to radiation pressure. So what happens as a star uses its nuclear fuel is it actually shrinks a bit and it collapses into a more compact configuration. And that shrinking, of course, increases the pressure and the temperature, which increases the burn rate and the fusion rate, and that, of course, leads to higher temperature on the Earth. So that's why stars burn hotter as they get older. They're actually settling or reconfiguring themselves according to hydrostatic equilibrium, and it implies a small amount of shrinkage and a small amount of net heat gain.
All right, the next question is from Stefan, who asks, the ecliptic line on star maps is a thin line and the projection of the sun's trajectory. But in the summer, the sun is higher, and in the winter, it's lower. So how does this work? Is the line an average calculation?
No, the line is a particular track. It's a particular trajectory of the sun. As you say, it's the projection of the sun's path across the sky. The complication, of course, is that the Earth has a tilt of 23.5 degrees on its spin axis. So the ecliptic line cycles through a year. It arcs in and out of the terrestrial equator, the projection of the Earth's equator into the sky, and the angle between those two lines where they intersect is 23.5 degrees. And that's what leads to the sun's migration in angle in the sky over the seasons by a net amount of twice that angle of 45 degrees. 45 degrees, or twice the tilt angle of the Earth as it orbits the sun, is the change in minimum and maximum elevation of the sun over a full cycle of the seasons.
The next question is, pardon me, okay, from Hernan, who has kind of a follow-up. You mentioned habitable zones for exoplanets, but in our solar system, life could well exist in non-habitable zones, like on Europa or Titan or Enceladus. Why do we always stick to this habitable zone terminology?
Right, it's a good point. Habitable zone is a very particular definition, and it's a somewhat limiting definition, and it excludes some real possible places where life might exist. But astronomers now have, broadened their ideas of this, of course. It's just a convenience when you're talking about large numbers of exoplanets and their stars to calculate as a first instance the habitable zone outward from that star. That is to say, a range of distances where water could be liquid on a surface of a planet. Now, the habitable zone is idealized right away because that just is based on an equilibrium temperature where radiation hits the surface of a rocky planet. It then depends, of course, on the albedo. So the temperature on the planet depends on how much of that radiation is reflected by the planet as opposed to absorbed. So that's one modification of simple habitable zone idea. Second modification is that the planets will have atmospheres, and those atmospheres are likely to have greenhouse gases or heat-trapping gases like methane or carbon dioxide, and that will raise the temperature beyond that equilibrium energy balance calculation. So habitable zone is already got to be modified two ways, even in the classical definition of a planet around a star. But of course, astronomers know that there is a thing called a cryogenic habitable zone, which in the solar system example means the moons of giant planets, which could be habitable because they have sufficient energy in the interior, or they have water on them, or there's water that could be kept liquid under pressure from rocks and ice on top, and these are all well beyond the classical habitable zone. So the solar system, of course, tells us about the cryogenic biosphere and the fact that the habitable zone definition must be relaxed. And in the end, you actually need some sort of an operational definition to move forward. So for exoplanets, we're using one definition, and for planets and moons, we're sort of using a different definition. Remember that we still have not detected any exomoons, 0. So as soon as people are able to detect moons around giant planets, around other stars, then we'll have to have another iteration of this definition.
Excellent. Another live viewer has a question I think is really interesting. I don't think we've covered before. Are there unique minerals on other planets, meaning minerals that don't occur on Earth but do occur in other locations?
That's an interesting question. Um, we think that chemistry is universal, so we're pretty confident from spectroscopy in other galaxies and 90% of the way back to the Big Bang across the universe that the chemicals and the chemical ingredients in the periodic table are universal. We see those same elements. So we've never seen an element that we can't identify. As far as compounds, minerals, and molecules, that's a little more interesting. We might imagine that the abundance of molecules that have been discovered on the Earth and the incredible variety of minerals would accommodate all the different variations that might be found in the universe elsewhere. But that's not actually true. We don't know that for a fact. So I would say it's possible that there are indeed minerals on exoplanets or on moons around other planets that are not familiar to the Earth. But as far as those we've investigated, those places where we can actually investigate minerals, we have not found them yet. And that, of course, means in the solar system. So we have moon rocks that we've scrutinized in detail that we brought back by Apollo. We have Martian meteorites that we've studied, and none of the minerals found in those objects are alien or not found on the Earth. For exoplanets, it's much harder because we simply don't know what exoplanets are made of. Our measurements of them is too crude to know what the minerals on those exoplanets are.
The next question we have is from Jeff and Raja, who asks, how do scientists, excuse me, how do scientists measure the distance between the sun and the moon and the stars?
Well, the distance to the sun was actually measured at first time, I think, 250 years ago. It's called the solar parallax. And it was a difficult geometric experiment that was done with telescopes of the time, where you're essentially defining the triangle made by for the Earth's diameter, defining a small triangle with the sun at a distance of 150 million kilometers away. So that was the way the distance to the sun was first measured. The distance to the moon and the planets were measured in a similar way by just trigonometry, basically. Once you've trigonometrically measured the distance to any planet, then you can project the distances of all the others by Kepler's law, because Kepler's law has a fixed mathematical relationship between their distance and their orbital period. And the first planet that was directly measured by trigonometry was Venus in 1761 and then 1769 in 2 transits of the sun. So that historically is how we measured the distance to planets and the moon. Now, modern day, we have better tools. Since the Apollo astronauts left behind reflectors and magnetometers on the moon's surface, we now actually measure the distance to the moon by a laser altimetry, by a bouncing laser light off the moon. And that's how we know the moon is getting 4 centimeters further from the Earth every year.
The next question is from Isla Hollyrod, Holroyd, who asks, can you tell us what you think about the recent radio signals that were received that seem to be emanating from the center of the galaxy? Is there any significance to these or pattern in the signals?
Yeah, this is an interesting result, a very recent research result from an Australian radio telescope array, finding sort of pulsing, not periodic though, but sort of episodic radio signals that appear to emerge from the center of our galaxy. I think they've so far ruled out pulsar as the cause. It's simply just not a repeatable pattern in that way. They would have to have a strict periodicity to be a pulsar. So it's a somewhat more chaotically variable radio signal. And the answer is we simply don't know. This radio telescope does not have the precision to pinpoint the source of the radio waves extremely accurately, unfortunately. It's a very sensitive radio telescope, but doesn't have super angular resolution. So that's going to make pinning down the source very hard. But it does appear to come from the galactic center, and we know there's a 4 million solar mass black hole there, and a lot of chaotic and energetic phenomena associated with. So the speculation is probably going to be that these radio signals come from the fueling zone around the center of our galaxy's black hole. but at the moment it's still a mystery to be solved.
All right, the next question is from one of our live participants. Alan asks, why is there a constellation called Andromeda and a galaxy called Andromeda?
Well, it's tradition to name objects by the constellations they occupy. So the constellation came first. There are 110 constellations that the International Astronomical Union has sanctioned as official constellations. The historical number was 88 constellations, but it's grown over the centuries. And it's common to name the brightest object by the name of the constellation. So 2 examples would be 61 Cygni is the 61st brightest star in the constellation of Cygnus, and Cygnus X1, which is a black hole, is the brightest X-ray source in the constellation of Cygnus. So it's fairly common for visible astronomy, radio astronomy, and X-ray astronomy, if you have a sort of singular object in a particular part of the sky, to name that singular object in some way after the constellation that it occupies.
The next question is from one of our live participants again, who asks, when do you think we will be able to observe or detect atmospheres on planets outside our solar system, and at what level of detail can we analyze them?
So we have already been able to detect atmospheres around exoplanets, and this is done by a sort of shadowing or back illumination experiment. I mean, basically, you have an exoplanet, it's a transiting exoplanet, and as that exoplanet passes in front of its parent star, the starlight is partially blocked by the body of the exoplanet, but some of that starlight filters through the edge of that planet, through the limb or the atmosphere of that planet, and that imprints absorption features on that part of the light. And then as the planet goes around behind the star, you can just do a subtraction or a differential experiment. That method has been used in more than a handful of cases to actually sniff out the chemical ingredients of planetary atmospheres. So far, this has only been possible for hot Jupiters and occasionally a super Earth or Neptune-sized planet. So it's not really been done for an Earth-sized planet because that's very hard. And in those experiments, we've seen what we'd kind of expect to see. We've seen sodium, trace gas, potassium. We've seen water vapor or steam because it's a very hot planet. I've seen carbon dioxide, I think carbon monoxide. So various chemical constituents of these atmospheres have been seen. So it's a well understood technique, and it's just going to be done better and better. And I think within a couple of years that technique will have worked its way down to terrestrial planets. And at that point, people will start to look for biomarkers, which are atmospheric gases that indicate a metabolism or biology, microbial biology. And for the Earth, of course, that would be oxygen and ozone and methane. You probably need more than one biomarker gas to be sure you've detected life. But those experiments are coming, and that experiment is already doable, and people have been testing out their techniques with more massive planets, with the terrestrial planets or the Earth-like planets still to come.
All right, it's 11:04. I had some technical issues, so I think we can take at least 1 or 2 more questions, depending on your availability, Chris.
Yeah,
so we'll take it.
Couple more.
Okay, we'll take at least 1 more question. So this next question is from one of our live participants. It's related to the atmosphere questions. So when or why do some objects or planets have atmospheres and others not?
Retention of a planetary atmosphere is purely a function of gravity and mass. Now, of course, how planets get their atmospheres in the first place is a more interesting question. So when planets form and they're young and hot, there's a lot of outgassing. There are hot gases released from the interior of the planet. For example, early in the history of the Earth, there was a lot of hydrogen deep in the core that was released, and it was a light gas, so it was not retained by the Earth's gravity, so that hydrogen escaped into space. But after a planet solidifies and cools, then the kind of atmosphere it will have and the thickness of that atmosphere definitely depends on its mass, because the gravity is what's holding that gas to the planet. But there's going to be large variation between planets. We also know that the composition of an atmosphere can change over time. Mars, for example, is much less massive than the Earth, substantially less massive, and it is less able to retain its atmosphere. And so there's very good indication that Mars has slowly lost its atmosphere over time as it bleeds off into space. That same process is happening at a very much less level for a planet like the Earth or Venus, but these are similar sized planets that are able to retain the atmospheres of the composition they have. So the short story is that the light gases tend to leak off into space very early in a planet's history. The more massive or heavier gases or bigger molecules are retained unless the planet is substantially smaller than the Earth, in which case it can't hold an atmosphere. And then you get down to bodies the size of Mercury or the Earth's moon, which have insufficient gravity to hold any atmosphere at all.
All right, the next question is from KV Geldrin, who's on with us live. When we observe something that is 100 million light years away, don't we actually see something that was 100 million light years away, since the universe has expanded since then? And if that's right, is there a way to measure what the current distance would be at this time?
Yeah, it's a good question. Not only do we see an object that was 100 million light years away, we see the light as it was 100 million years ago. So we're seeing old light, and we're seeing an object that's no longer where it was when the light was emitted. That's a little confusing. The question of what it's doing now and where it is now is answered simply by the expanding Big Bang model. Given our measurements of dark energy and dark matter, we have a model for how the universe expands over time, and that lets us sort of connect the dots of an object that we observed, say, 100 million years ago. How big was the universe then? And it's taken 100 million years for that light to reach us. How big was the universe now, 100 million years later? So we can calculate that using the Big Bang model, but we're stuck with the fact that the light we observe is old. Distant light is old light, and there's nothing we can do about that. So we can't answer the question, what is that galaxy doing now? Because we can't see the galaxy now. We always are left waiting 100 million years to see the light and the information. That's a good question to end on, and thanks very much for your patience and for good questions as always. And we're back in the swing of things, so we have a time set up that you'll hear about that's 2 weeks from now, and we'll try and keep a normal cadence through to the holidays.
Excellent. Thank you, everyone. And I did find a mistake, or one of the students found a mistake in my email. I accidentally said that the next live session will be on Wednesday, the 28th. The 28th is actually Thursday. So 2 weeks on Thursday, October 28th. And so for those of you who have time zone questions, it's now 11 o'clock in Mountain Standard Time. We start at 10 o'clock Mountain Standard Time or Pacific Time.
I think clocks change early November or something.
Yes, that's correct. All right, so take care, everyone. We are excited that you could visit us today, and we'll talk to you again soon.